I'm well aware that most people only watch the first 30 seconds of a YouTube video, and this has quite a technical topic, so here's the 30-second summary. We can make a quick initial aircraft design using the Blender tools that I've documented previously. Using the free add-on, we can export the design data for the flying surfaces to XML files which can be imported into the free xFlr analysis software. We can then investigate many aspects of the aircraft's performance such as efficiency, stability, glide angle, CG location, and a lot more. It's easy then to flip backwards and forwards between Blender and xFlr5 to optimize the design. So that's a quick summary. I'll now take a little while to go through the mechanics of the actual export and import process, and then I'll do a case study for a particular design of a glider. I'd like to just say up front, if you're watching this video hoping you can use the add-on to import, say, an STL file from another program and then immediately export it, I'm afraid this won't work. The add-on doesn't export the actual wing geometry directly. It exports the airfoils, the twist, the planform shape and the dihedral data, which the Blender geometry node tools use to build the wing shape in Blender. It's not all bad though, as long as your wing design is reasonably conventional. It should only take a very short time to recreate it in enough detail to do the export. xFlr5 is a free and open source tool that builds on another tool called xFoil. xFoil is used to calculate the data that you see displayed on websites like AirTools, and it works in a 2D way for a given airfoil shape. xFlr5 expands on this base to analyse the characteristics of a three-dimensional aircraft. To do this and not require weeks of time on a supercomputer using a full CFD analysis, it uses models with a lot of assumptions and limitations. It'll work best on larger models and particularly higher aspect designs, like gliders for example. However, for me, the real value has been what I've learned about aerodynamics as I've tried to wring some sensible results out of the thing. To download xFlr5, go to the homepage. I've got a link on the video description. The latest version is 6.59, and it downloads as a directory with a Windows executable. It's also possible to get a Linux version running. It is a little less straightforward though. I feel the main focus of this video should be to document how to download, install, and use the add-on that I've made. It's pretty straightforward, so I'll spend the next 10 to 15 minutes or so doing just that. Then, although I'm anything but an expert on xFlr5, I think there would be some value if I worked through some case studies of exporting simple examples of plane designs and trying to extract some useful information from the analysis. The xFlr5 add-on is included in the zip file with the Design Tools Blender file. Let's go to the 3DP Plane Design GitHub page that you can find linked in the YouTube video description, and then click on the download link that appears after the words Blender File Download. We'll navigate to the downloaded file and unzip it, and there should be one blend file that contains the geometry node tools and two add-on zip files. These zip files, they should stay zipped. That's how Blender add-ons are distributed. The first video in this series showed how to download the latest release of Blender, so I'll assume you have this installed. I'll start Blender and then select the Preferences from the Edit menu and then Add-ons. Click the Install button and navigate to the FLR5 export zip file that we downloaded earlier. The add-on should appear in the list and we'll enable it by the tick here. If you've downloaded the 3DP Plane Design zip file previously, please note that any version less than the 2.15 version won't work with the latest Blender version due to some changes in the API that I hadn't realized about. Okay, now let's file and open the 3D plane design file that we just downloaded. First up, although xFlr5 does support a simple fuselage, the documentation recommends not using it. The problem is the interface between the wing and the fuselage. If they intersect, then there'll be a runtime error. However, if they don't intersect, the software will assume the gap is real and there'll be vortices and incorrect flow paths, and the effect is worse than simply not having the fuselage. So, no fuselage. I'll make that invisible. But the gap between the wing halves is no good either. I've thought of trying to approximate a fuselage with the wing planform settings and then setting the twist to that section to make that area non-lifting. But actually, I think that would probably place too much incorrect emphasis on the impact that the fuselage would have on the lift of the wing. We could just extend the root area, but I'm thinking it's best just to move the two pieces of wing together to keep the total wing area the same. The export add-on doesn't pay any attention to the wing joining features of the wing v2 object, like the shrink wrap and the X and Y angles, so I'll just turn these off just to make it clearer what's going to be exported. Also, xFlr5 probably doesn't need as much geometry information as the 3D printer does. If you do export detailed geometry, it'll spend more time doing its calculations. If we use the wing v2 object to export, the add-on will use the number of ribs in the three different sections. The older wing object could also be used. It'll just then use just the main and the tip rib counts. We'll use the wing v2, but I'll drop the rib counts down to give us some coarse geometry to start with. The add-on uses the airfoil data referred to by the root and the tip airfoils. xFlr5 needs to know the airfoil shape of every rib along the wing. It can handle if the shapes are scaled by the shape of the wing or if they're twisted by the twist curve. Therefore, if we set the root and the tip airfoil to be the same, the add-on will export only one airfoil shape. The xFlr5 calculations will also be much simpler and faster because of this. Let's start with that for this example. Now, an important item. If the root and tip are different, the airfoil shapes themselves must have the same number of vertices, or else the export will fail. The add-on needs to morph between the two, and it isn't smart enough to do this if the vertex count is different. Since version 2.15 of the Blender plane design file, I've attached a geometry node modifier to each of the airfoil objects to allow resampling to a specific vertex count. You just have to enter the number of vertices you want for the airfoil, and then apply the modifier. If you do this to both airfoils, it's easy to make them exactly the same. The add-on will pay attention to the leading edge curve, the trailing edge curve, and the twist curve. I plan to also make it use the thickness curves, but the current version doesn't support that yet. In fact, just to be clear, the export add-on doesn't really look at the wing object itself at all. It just looks through the list of modifier parameters to find the right guide objects and parameters. So we can export the wing object by selecting it and clicking on the File, Export, xFlr5 Export menu. It'll ask for a file name and a location, and I'll put main for the main wing. Once I've done an export, an xFlr5 panel is available here on the right-hand side of the viewport. It'll allow me to select the size of the analysis panels that xFlr5 uses, and it's measured as the number of panels per meter. The default is 100 per meter, or that means 10 millimeters square. That's a lot of panels to start with, so I'll change this to 10 and export again. Each analysis can take a long time if you're not careful, and we can ramp up this number later if we want more accuracy. I'll navigate to the destination directory to see the result. There are two files, a DAT file containing the airfoil data and an XML file containing the structure of the wing. If we open the XML file in the browser, we can see the information in it. It's pretty straightforward. There's a header and then information for each section of the wing. Let's jump back to Blender and we'll do exactly the same now for the tailplane and the fin. I originally had the plane exporting in one file, but I found it way more convenient to do it surface by surface when you're making lots of different design iterations. I'll run our downloaded copy of xFlr5 and I'll start a new project. From the module menu, I'll go to the xFoil Direct Analysis page and open the DAT file from our Blender export. We could flip to the Foil Design module to see an outline, and we could also do some basic editing there if we wanted. Now to the Wing and Plane Design module. I'll go to Define a New Plane. The import options on this page are not for use for us. This program has a lot of ways to save and restore analysis results, but they aren't compatible with external programs. Instead, we'll click on the Define button for the wing and go to the Other pull-down and select Import Wing from XML file. I'll select Save to save the wing, and then we're back on the plane design form. And now we just have to do exactly the same with the tailplane and the fin. Note that we'll have to get rid of the default X positions of these two objects, and also, unfortunately, xFlr5, the import from XML file, just doesn't read the vertical location of any of the objects, so we'll have to import this data manually. And we're done. We can save the project at this point. We can read the manual and all the other reference material and analyze to our heart's content. Okay, let's look at a real case study in using the Blender tool and xFlr5. I'm definitely not an expert in either aircraft design or xFlr5, so please take what I say with a grain of salt, and if you have more experience in these areas, please feel free to comment on the video. I've been thinking about making a slow motor glider that I can use at a sports field near my house and try for some thermals. I'll try designing it from scratch and, as I'm no expert, I'll ask the internet for some initial basic parameters. I'll go quickly through this bit as I've covered it in the other videos. I'll start with a wingspan of 1.5 meters. That's a bit bigger than I'd like, but I think I'll need it that big to get good performance, but then I can try scaling it down to see what changes. The internet says that an aspect ratio of 8:1 is quite common for balsa gliders. Might be a bit high for 3D printing, but I'll try it. It gives me a wing area of 28.1 decimeters squared. The internet says the cubic wing loading should be under 4, and a weight of 500 grams gives me 3.3, so we'll try that. For an airfoil, RG15 is commonly mentioned, but it is said to be a fast airfoil. An SD7037 for the wing might be better. For now, I'll keep the airfoil the same right to the wingtip, but I'll probably change this later. I'll use NACA 009 for the tail and fin. So what's a good spacing between the main wing and the tailplane? Not a lot of internet advice on this, but somebody says 2 wing chords, so I'll try that. The tail aspect ratio should be quite a lot smaller than for the wing, so perhaps 4 or 5. A tail volume of 0.5 and a fin volume of 0.02 is suggested, so that gives me the tail area. I'll give the main wing some dihedral and sketch out a rough fuselage shape. I'll set the angle of incidence of the main wing to 2 degrees. Just remembering the twist curve is scaled as downwash, so minus 2 degrees is equal to a positive 2 degrees angle of attack. And I'll set the tailplane angle to 0 degrees, and that will give just a slight difference between the tailplane and the main plane. I'll also check the resolution of the wing model, and this is about right. We don't want too much detail in the wing, or else it'll take a long time to do the calculations in xFlr5. I have a rib count of 6 and a root rib count of 3, and that should be about enough. So now I'll export the wing and fin surfaces to XML files as we detailed in the previous section. So I'll go fairly quickly through this. And I'll load up a clean copy of xFlr5, and I'll import the information. First we go to the xFoil direct analysis or foil design, either will do, and I'll import the 3 DAT files. We can view them in the direct foil design module, and there should be 1 cambered style foil and 2 symmetrical foils for the tailplane and the fin. Now I'll jump to the wing and plane design and I'll generate a new plane. I'll give it a weight of 0.5 kilograms as we discussed previously. And we will import the main wing, the tailplane and the fin by going to Define, then Other, and Import by choosing the appropriate XML file. I'll have to zero out the X offset for the tailplane. We don't need that, but I do have to add a little bit of Z distance because, unfortunately, the import function of xFlr5 just doesn't seem to work on these vertical distances. And the manual also recommends that the tailplane not be in line with the main wing. The tailplane has to be lifted out of the streamlines of the main wing, or else there can be calculation errors, so I'll do that. We'll save that, and I'll give the plane the name of Basic. And we're ready to go. I'll jump back to the xFoil direct analysis, and the thing we have to do is generate polars for the 3 foil sections. I'll just do that for the main wing first, and we can define a batch analysis. We'll choose a T1 analysis, which is basically just running through a bunch of Reynolds numbers and also a set of angles of attack, or alphas. And that will produce the 2-dimensional data from which xFlr5 will generate a lookup table. The Reynolds number for an airfoil is large if the aircraft's moving fast and for large areas of wing, and it's small, of course, for smaller sections of wing and for slower flying. I'm not sure this range will cover everything perfectly. 30,000 isn't particularly small, so I'll just do a small amount of editing and I'll try and cover the smaller Reynolds numbers for this sort of aircraft. We just have to decide on an angle of attack range to analyse. Bearing in mind I'm going to use the same range for both the tailplane and the wing, I have to include negative angles of attack, and perhaps I'll go as high as 10 for the situation close to the stall condition, and I'll keep the default increment of 0.5, although there is an argument of making it smaller for more accuracy. I'm going to press Analyse, and it will run through and do the calculations for the main wing airfoil. And we can see them in this information here. I can go to the graphs and view just the lift versus the alpha, and we see the curve we expect. As the angle of attack gets greater, the lift gets greater. However, for small Reynolds numbers, which are down here, you can see things get a little weird, and that's pretty common for small Reynolds numbers. I might also go to the options in Preferences, where there are quite a lot of options for things to display, and I might unclick the flow down changes, which because that gives one colour for each airfoil, it's a lot easier to follow if each line's a different colour. Now the important thing here is to make sure that we have a wide enough range of Reynolds numbers and angles of attack, because xFlr5 will look up and treat this information as a lookup table. So any region outside of this range will cause errors if the numbers that are needed in the calculation aren't present. We'll also have trouble with the low Reynolds numbers where the airflow separates and we can have big differences between the different lines. And when it comes to interpolate the data, things can go very wrong in these sorts of regions. But we'll try this for now, and if we get too many errors, we can come back and look at this later. So what I'll do is just go back to the batch analysis, but this time I'll hit the Control A to select all the airfoils and do the T1 analysis for all the Reynolds numbers and alphas and just wait for the result. It doesn't take too long when we've only got the 3 airfoils. It's going to take longer when we have different airfoils for the tip. So that's the end result of that calculation. Having done that, we can just jump back to the wing and plane design and perform an analysis on this. It's quite similar to the 2D analysis. We simply go to Analysis and define one. And we have a choice of the polar type. We use type 1 for the xFoil analysis, but here I think we'll choose type 2, which is fixed lift. So this lets you analyze the conditions of getting exactly the same amount of lift as the weight of the aircraft. And that's good for analysing a glider's performance. It also gives some insight. It makes it easier to find the correct operating point where the plane is flying in a level flight. The analysis will choose the default, which is the vertex lattice method. The manual says there's very little difference between the horseshoe vortex and the ring vortex. The lifting line technique is only valid if we only had a wing and not for the entire plane. We'll choose the plane inertia, which we already entered as 0.5 of a kilogram, and we'll just accept the default viscosity for the air, etc. Then, like the batch analysis for the airfoils, we can analyse this over a range of alphas, or angles of attack. And so I'll choose from an angle of, let's say, -2 up to an angle of 8. And we can come back and review this if it doesn't give us the information that we want. So I'll choose Analyze, and we'll sit back and wait for this to happen. And almost always there will be errors. They just seem to be inevitable. And sometimes they're quite important, and they're mostly dealing with values that can't be interpolated. So the analysis of lift for a particular section of wing, perhaps it needs, for example, a coefficient of lift of 1.2, and the graph just can't provide that number. In many cases, this isn't very important, and you can see this at 8 degrees, which is we're unlikely to be flying at because it's too close to stall. And generally, what I would do is look at the polars, and if we get the type of information that you expect to see, then probably the errors aren't particularly significant. But before we finalise the design, we should go back and just try to check that we're not missing something important. There are various polar graphs available. For example, we have lift versus drag, and the lift-drag ratio versus the angle of attack, and other information like the pitching moment versus either alpha or speed. We can view this from an aircraft point of view and see graphical information like induced and viscous drag. The default scaling seems to be wrong. I'll have to find the right menu to adjust this. It's the 3D scales menu where I can adjust the scaling. So we have induced drag and viscous drag, and we can select which angle of attack is being shown, and we can get a graphical feel for the forces involved. We can also show things like the stream flow and the downwash information. You can see with an alpha of 6, we're getting downwash from the main wing and also from the tailplane, so the tailplane is lifting at this operating point. We can see the lift distribution along the wing, and we can see this more clearly if we go to the span-wise polar view. If I show just one graph at a time, I can use the numbers 1, 2, 3, and 4 to bring up different graphs. It's a little confusing with so many lines, so if I go to the operating point and show just a current operating point, it will show me one point for a given angle of attack, and this is the type of information that can be quite interesting. This is the induced angle, which shows how different the angle of attack is along the wing due to the outwash of the air that runs span-wise along the wing. you can see towards the tips of the wing, the airfoils are actually seeing an angle of attack that's 2 degrees different from the angle of attack in the middle of the wing. I can hit the number 4 key, which takes us to the local lift diagram. And this is where theory says that an elliptical lift profile will give the least induced drag. And in the op point menu, we can select a target elliptic curve. I'll reset the graph scaling using the R key, and we can see how our wing local lift curve is comparing to the optimum elliptic local lift. It's not surprising that our wingtips have way too much lift, and that's because we have no downwash at the tips, we don't have an elliptical wing shape, and because of that we'll be incurring additional induced drag over and above what we need to. Let's go back to the polars and have a slightly closer look. I'll select the 4 graph display and we can change the scales to suit ourselves. I think it would be more interesting to go to the current graph defined graph settings using the G key, and instead of plotting the efficiency against alpha, I'll plot it against the speed of the aircraft, V. I'll change the operating point to the best lift-drag ratio, and we can see the best glide angle is occurring at 6.8 meters per second. That's the most efficient speed when gliding for distance. It's not the only type of information we might want to see for a glider. We can also select the vertical speed VZ versus the airspeed V, and that's another way of looking at the glider's performance. This is the sink speed, so the lowest point in this curve is the slowest speed at which the aircraft is descending towards the ground. You can see it isn't at the same speed as the best glide angle, it's the operating point that will make the glider stay longest in the air. So, for a thermaling aircraft, when you're in a thermal, you're likely to be wanting this operating point, and when you're out of the thermal and travelling to another one, you probably want this other operating point. What else can we see with this information? We have the pitching moment, and we can see this has a negative going graph. So as the angle of attack goes up, the more negative the pitching moment becomes and the more nose down the aircraft wishes to go. A negative slope is a good indication that the aircraft is stable in this configuration, because if there's a slight upset and the angle of attack increases, you can see the operating point moves down and the aircraft tends to be more nose down. It's a self-correcting behaviour. If the slope of the line was an increasing one, and we're at an angle of attack of, say, 4, and a disturbance pushed it up to 5, then the aircraft would want to nose up, and it would be unstable. We can also plot the pitching moment against airspeed. It's interesting because if we look where there is zero moment, that is, when the aircraft neither wants to tilt up or tilt down, it's the airspeed where the aircraft would travel on a level path with a neutral elevator setting. You can see this is occurring at just a little over 10 meters per second. Let's jump back to Blender and we'll go to the tailplane twist curve. I'll select it and we'll give it a little bit of up elevator in effect by increasing the downwash on the tailplane. Let's try 1 degree of downwash. We can export the tailplane back to the same file and import it again and rerun the analysis. We can see immediately the difference. Now the operating point is the aircraft is trimmed out at a 0.5 degree angle of attack, and we're just a bit faster than the best glide angle and with a faster sink rate. On the other hand, we're quite a long way away from the stall still, so perhaps I'll make one more adjustment. I'll take that to 1.5 degrees and export again. Now the operating point has zero rotational moment at 1 degree angle of attack, and that's happening at 7.8 meters per second, which is getting closer to the best glide angle. Let's leave that there and see if we can improve the overall drag by trying for a more elliptic local lift curve. Back to Blender, we'll look at the planform of the wing and try for something with narrower wingtips, which should have the desired effect. I can use the 3D Print Toolkit add-on to look at the total area of the wing, and I know that it was 58 decimeters squared before, which is effectively double the wing area. So I'll try to keep the wing area and wing loading constant. I think that will be the fairest comparison with the original design. Okay, that's pretty close, and I'll also just streamline a little the tailplane and the fin. I'll also choose a different airfoil for the tip, and we'll make it a non-lifting airfoil that only affects the very tip of the wing. We'll go back to the wing, look at the tip airfoil, which is currently an NACA 2412. We can look for a symmetrical wing section. Perhaps we'll go for a 9% NACA 009. It only has 69 vertices and the root airfoil has 100, so as we discussed earlier, I'll just use the resample airfoil modifier to make that change. There, now it's been resampled to 100 vertices and the two airfoils will be compatible with each other. I'll just make sure that the root is set to the root airfoil and the tip is set to the tip airfoil, and we have to set the interpolate curve to make the non-lifting airfoil only apply towards the end of the wing. I can do that by adjusting the interpolate curve so that most of the curve follows the root airfoil, and if I adjust the curve in this way, only the last, say, quarter of the airfoil will be significantly converted to a non-lifting wingtip. Let's try exporting this again. We'll export all the surfaces back to xFlr5. And I'll duplicate the plane and call it elliptic. This gives us a way to compare the results of the analysis. This time, when we go to load the airfoil data, we'll find there's a lot more to load because now there's a separate airfoil for each part of the wing. So I'll open all of them up and we'll go to our batch analysis. I'll select all of the airfoils and analyze. Of course, this will take longer than before. Okay, we're done. There's a whole pack of information that's needed to interpolate the results from the 2D analysis. We'll jump back to the 3D design, select our new model, select the current plane, edit, and load up our new wing information. There, that looks like the revised aircraft. I'll assign an analysis. It will be the same type 2 as before. I'll assign an analysis. It will be the same type 2 as before and will run the same range of alphas. I'll go to the polygraphs and see if there's any difference. We do get a different analysis. We must have had some more significant errors this time because we only get a limited range of data. But we can see that the efficiency of the wing has in fact increased. It's not particularly spectacular. It's gone from 16.3 lift-to-drag ratio to 17, and it also has a slightly improved rate of descent. It's going from just 0.37 in the vertical direction to 0.36, and if we look at the span-wise local lift at its best lift-to-drag operating point, then we can see we've come much closer to our desired local lift characteristic. We could go back into Blender and fiddle with that, say the twist curve and tweak that, but the results aren't overly dramatic, so I don't think we have to worry about it too much. So let's check the trim for our revised model. The pitching moment does cross the zero line at a very similar point to before, so we're looking at a speed of 7.6 meters per second, and that's a fair way up the curve from the optimal point again, so I might make a quick adjustment to Blender and adjust the tailplane to give some up elevator so the trim speed is reduced. I'll do the analysis again, and now we can see that the zero crossing point is quite a bit slower, and that's very close to the optimum spot on the lift-drag ratio. The reduced data that we get is likely to be due to the small Reynolds numbers towards the tip of the wing, due to the more elliptic shape, but it still gives us some data in the area of interest, and we could look into the errors if we needed to. Now, another thing we could look at is the location of the neutral point of the wing to help us set the CG. What we can do is to try moving the weight forwards and backwards in this simulation until the pitching moment is a flat line with no increasing or decreasing slope. This is a point for the aircraft where if there's a small disturbance, the plane doesn't try to either return to the original flight or to become totally unstable. Now if we edit the current plane by going to the plane inertia and choosing a different value for the position of the CG, I had originally chosen 0, which back on Blender was the quarter distance along the chord. So if I go a bit more towards the middle of the wing, let's say minus 0.05, then we'll see what happens. I'll save it, and if we look on the plane view, we can enable the mass indication to make sure it ended up where I expected. We can go back and run that analysis again and look at the polars, and you can see that there's just a slightly rising curve, so we've gone back just very slightly too far. I'll edit the plane again and make it 0.04 instead of 0.05, and so move the weight very slightly back towards the front of the wing. Now that's a slightly negative curve, so we're pretty much located on the neutral point of the wing. The correct location of the centre of gravity can be estimated from that information. The static margin of stability for a wing refers to the distance between the CG and the neutral point compared to the total mean average chord of the wing. Something like, I don't know, 10% might be acceptable for this type of glider, although it's a personal preference. So we can move the CG forward just a bit. We won't put it quite back where it was, but perhaps we're going to have it at, say, 0.02. And now the wing will be somewhat less stable than it was before, but it will be a little more efficient. We can run the analysis again and compare it against the settings before, and in fact, you can see we have scored just a little bit of an increase in the lift-drag ratio, and we still have a negative curve. I'm not sure I trust that sudden drop in lift, but I think the fact we had those errors before were telling us things aren't very clear at that range. The change in CG has affected our trim, so now we've gone right down to the bottom, running at an alpha of 5, which is way too far on the stall side of the curve. So we have to take back of some of what we did with the elevator setting. Instead of 3 degrees, I might go back to 1 degree and export and import. And analyze. And we're still slightly too slow, but you can see we've actually increased the performance quite significantly in both the descent rate and the lift-drag ratio from our original basic design, and we've come up with a slightly better position for the centre of gravity. We do have one little issue here, which is if we plot the moment of rotation against the angle of attack on the wing of the entire plane, you can see that the operating point where we're nicely trimmed, we're operating at nearly 5 degrees angle of attack. And the trouble with that is, if we look at Blender from the side, that means the plane will have to be tilted up and the fuselage won't be pointed directly into the airstream. The solution is simply to give the wing more angle of attack, and I'll do exactly the same for the tailplane so that they stay in the same angle relationship. Hopefully that means the neutral trim position will be at a 0 alpha, which means the fuselage is pointing directly into the wind, assuming we designed the fuselage to be at its most aerodynamic along the y-axis, of course. I can do that by subtracting 4 degrees of downwash on both the main and the tailplane. You can see the effect that it's had on the two flying surfaces. I'll export them again and import and analyze, and we can see the other parameters haven't changed. The other polars haven't really changed significantly, but now what happens is the operating point where the plane is neither tilting up or down has changed. Instead of being around the 4 or 4.5 degrees alpha, it's now 0 degrees because we've tilted the wing further on the model. So for this model, I think I've covered enough things. There are so many more things that we could look at. Just for example, we could look at the force in the x direction versus the speed, try and get some feeling for the thrust as the airspeed increases, and many other things. However, that's a start. I hope this gives you some idea of how to use the Blender export function in conjunction with xFlr5.